Can you hear me? Good? Yes? Okay. Ta-da! All right. Okay, good. So, my name is Andres, and I work at Syncom. I write virtual machines, and in my free time I organize conferences, I don't know if you noticed, and I also write books and things like that. I heard that some of you may have some interest in my books. If you do have such interest, just let me know after the talk and I'll be more than happy to talk to you. So today, why am I giving this talk? Because when I started writing Smalltalk code, most of my work was on the image side of the house. And on the image side of the house, many wonderful things happen. Like, for instance, I don't have to care about garbage collection. I don't have to care about dealing with the operating system's idea of file handles, socket handles, memory management, and all that kind of stuff, which is very nice. But in the last few years, I moved from the image side to the virtual machine side. And at times it's been kind of a rude awakening of all the things that I was blissfully ignoring. And what I learned in the process is that it is sometimes dangerous to ignore some of the things that we're going to talk about today. But it's really difficult, I also found, to just walk to a typical small talker that deals with the image all the time and just tell him or her, oh well, because there are all these problems. Because when you work on the image, there's hardly these kinds of problems. There's hardly an equivalent with which the conversation can revolve around. So it's difficult to communicate. So this is my attempt at bringing some attention to some of these problems that I think can be pretty serious. So, with that spirit, so everybody knows, behavior in Smalltalk, we have this wonderful cloud of objects, and they send messages to themselves and each other, and you write to another cloud of objects, the one on the right, and behavior could be seen as a function that maps one state to the other. And we all know this, we all know all objects and message sends and all that. But when you're dealing with C, things are kind of not quite the same. So you have basically this chunk of memory in a big papyrus with instructions that say, oh, now do exactly this, now do exactly that, now do exactly this, now do exactly that. And unlike in our object world, there's not so much of a boundary between things. And so it's very easy just by passing pointers around to start violating what we in Smalltalk would call encapsulation. And we know the problems that this causes for us. I mean, if we were able to, say, get an object and without sending it a message or just mess with its internals, chances are we wouldn't look at it in a positive light. But in C, this can be normal. Sometimes what it's not so clear is that really Smalltalk is also a C program. And perhaps this is news to you. At times it feels like it was news to me, that indeed it is a C program. And this C program, which we typically call the virtual machine, makes as if all these objects actually exist and pretends that actually messages are sent and so on. But really, we're talking about a big chunk of memory and a papyrus. And the point here is these two things are not the same. And this is where things get complicated, because of course, we would always say, well, of course C is not the same as Smalltalk. That's why we typically use Smalltalk for anything that is more or less complicated, because it's so much easier to use. But because we use Smalltalk most of the time, I think, from my experience, and my experience trying to explain this, it's sometimes hard to point the finger at what's different and what's the implication. So let's start with some vocabulary, because if we don't have the terms, it's really difficult. So typically, as opposed to the image side, typically VM people will talk about things in these terms. Implementation dependent. What does that mean? Well, that means that some things have a defined behavior in some document, but the particular implementation of this specified behavior depends on the implementation of this particular behavior. And this comes up, for example, when you're dealing with, say, a virtual machine that runs on Spark, and you find out that the instruction LDD sometimes throws an exception and sometimes it doesn't, and that depends on the particular manufacturer of the chip, even though it is the same instruction. And whether this exception is triggered or not makes a big difference, because the spec also says, well, if this happens, then you must provide a handler, and if you don't provide a handler, then you should do this and the other, or your program crashes. So that's what we mean by typically implementation dependent. Now this, of course, causes problems for us VM developers, because now we have to, we cannot simply say, oh, it works on my machine. So this can cause problems. So then there's typically unspecified. Unspecified typically means that there is a piece of documentation that says, oh, well, when you do this, that, and the other, it may work somehow, and the end result may be unspecified. For example, if you go to the ANSI spec and go look for set add, if you do set add nil, I believe the spec says the result is unspecified. Or it may say the result is unspecified, meaning it should work or it should do something, but we're not saying what it is. Then there is undefined. Now undefined, it may sound pretty much like unspecified, but it's really different. Undefined means, oh, you did something, and from now on, you can make no assumptions anymore as to what the program is doing. So whenever you see the word undefined, all sorts of red flags should go in your mind and say, oh, this is really, really, really dangerous. Typical, let's say, a good example of undefined. Oh, we'll see a few good examples of undefined. But typically, for the most part, undefined means the virtual machine crashes, if you run into that. So quickly you learn to pay attention to this term. And finally, there's appears to work. And this is one of the phrases we use at work all the time. When things are really broken, but somehow manage to work, and it's sometimes hard to believe how this can happen. And this appears to work thing sometimes it can be seen as some sort of rhetorical, unnecessary rhetorical artifacts. But I beg to differ, and for that we're going to see an actual example of something we fixed in this release of VisualWorks. So appears to work. How about this? You have a VM test cases, you have your VM suite of tests, and you run them on 32 bits, and this is what you see from the headless SUnit test runner. You see, running test so-and-so, running test blah, 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 running the IEEE tests, everything passes, everything's okay, and the same happens in every 32-bit platform. And when you start testing 64-bit platforms, you see this. Assertion failure, the stack is not right. Now, if you don't run with the assert VM that prints those messages, you wouldn't see anything at all. So apparently, since all tests pass, everything is fine, right? Okay. And I was not comfortable with this. So I started digging around and see what's going on. Well, what are these IEEE tests doing? Well, some of what the IEEE tests do is that, VisualWorks actually has two sets of floating point primitives. It has a set of primitives that will fail as opposed to answering you nan infinity, and another set of primitives that will actually answer nan infinity. And so these tests switch between the two to make sure both work. And it appears that when you flip the switch, the assertion failure comes up. Okay, so you go take a look at the code, and the code looks more or less like this. And this is where it gets complicated. So let's see. So basically, this is the function that implements the primitive that flips the switch, right? So the first thing that it says is, hey, commit the primitive. What does that mean? Well, some primitives don't return immediately. Now this may sound kind of weird, right? I mean, you send plus, it returns. You send equal, it returns. You send identity hash, it returns. What do you mean a primitive doesn't return? Well, for instance, semaphore wait doesn't immediately return. Well, fine, you say, whatever. And certainly garbage collect doesn't immediately return either. But why is this a different case? Well, because when a primitive stops running, well, Visualworks has a native stack with all the native frames for all the message sends. So eventually those frames, while the process is not running, may be thrown off of the native stack. And if you read the process back, how do you know the process was stuck in an actual primitive as opposed to a message send, like send wait? Well, commit primitive creates a dummy frame for the primitive so that when you get the frame back, when the process is going to restart, you know, oh, right, I was in a primitive, fine, well, let's restart the primitive. And in this case, we need to do that because the next thing that happens is stabilize all stacks, meaning get rid of all the native stacks and put them all into normal object memory like it usually happens with smalltalk-80. And then, oh, remember what was the last context? Blow away the native code cache so the new primitives get generated again by the JIT. Then change the switch so that any new, so now there's no native code cache, right? So any new message send is going to cause messages to be translated by the JIT and you get native code and so on. And because we actually changed the switch now, we're going to get the new primitives. And then you say, oh, right, now that I flip the switch and there's no native code cache, then I just put the context that I had before on the stack and I just say, oh, return. Okay. And nothing seems particularly wrong with that. But the documentation in the VM says, whenever you return from a primitive that is committed, you must do it like this. Meaning, commit again with the actual result that you want to answer, and then do that long committed prim return, which does something different that doesn't really matter, but it's slightly different. So you think, oh, okay, well, that was the bug. Well, clearly, the stack was not being recommitted the way it was. So you say, well, okay, this is clearly wrong, so you run the test again. 32-bit, no difference. 64-bit, what do you think? Infinite assertion loop. What happened here? Right? What is going on? So, okay, now we need more digging. So typically, end methods look like this, right? You have a header and a whole bunch of native code. Now primitives, because some primitives commit, well, when a primitive commits, what does it mean? For instance, semaphore wait is a primitive that actually, when you get back to that process, you need to restart the primitive again from scratch. So again, the test is done, oh, does the semaphore have enough signals? If so, then yes, take the process, make it runnable, decrement the signal count, return, or something like that, right? But some other primitives just return, like garbage collect, for example. When you garbage collect, well, the same thing happens, you know, you commit to the stack, blah, 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 blah. And when you get the process back so you can actually return from the garbage collect primitive, you don't want to restart the garbage collect because then the garbage collect runs over and over again. So actually you want to return. But there's no bytecode boundary for those two states, right? Because from the point of view of the VI, of the image, there's only one bytecode that says, oh, call this primitive. And now we have two states for the primitive with the same bytecode. So, primitive native methods have two pointers that are stored at the end of that end of the native method. One is a pointer to the instruction that returns, and one is the pointer to the instruction that restarts from scratch. So far so good? It's kind of complicated, but so far so good? Any questions? Yes? Go. Okay. So the problem was that in 64-bit, well, native methods are basically 16 multiples of 16 bytes long, right? So the pointers, to find the pointers, what that code is doing is saying, oh, okay, well, from the start of the native method, go to the end, and then subtract 1, which would be 8 bytes, right? In 64-bit, pointers 8 bytes. Subtract 8, and then you get 1, and subtract 8 more, and then you get the other. Let's see what the code is doing. It's not rounding to 16. It's rounding to 8. Oh. And then you realize what's going on. Instead of returning, it's reading some garbage over here, as opposed to reading here first. It's reading some garbage over here, and then, oh, is it a restart? Well, actually, is it a... Oh, it's the other way, right? So it starts reading here, and says, oh, is it a restart? Yes. Oh, okay, so instead of returning, it chooses the restart, and goes back into the primitive, and that's what you get, an infinite assertion loop. So you think, oh, yeah, okay, this is obviously wrong. And then it hits you, right? How does this... Is there anywhere else this problem is? Well, in 32-bit, the size of the native methods is a multiple of 8 bytes, and the pointer is a multiple of 4, and yet, for I don't know how many years, this problem never manifested. And it's really broken. Like really, really, really broken. So, it appears to work. This is the meaning of appears to work. It's something that is absolutely broken, but Smalltalk has this wonderful ability to work despite this kind of issues.
Why didn't the assertion fail?
The assertion didn't fail because by miracle, what should have been aligned to only 4, because by miracle, this was also aligned to 8-byte boundaries, even though it was only meant to be aligned to 4-byte boundaries. So I don't know, maybe you make a primitive method with a particular failure code, as opposed to whatever failure code is there, and this native code changes a little bit in size, and these things don't match anymore, and then you get an infinite primitive loop. If that primitive commits. So this is an issue, right? Because these kind of problems are extremely sneaky, and they jeopardize the operation of the VM. Now, you say, well, okay, fine, this is a bug, right? It's my fault, or whoever's fault. But the problem is, this is how undefined can also behave. So let's take a look at an example of an actual undefined. Now, everybody knows the function free, right? Anybody doesn't know the function free? Everybody familiar with free? Good. So if you go to the spec, this is what the spec says for the single Unix specification version 3. The free function, blah, 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 blah. And that's perfectly fine. Now let's take a look at the keywords that we spoke of before, like undefined. Well, for instance, if the space has been deallocated by a call to free, the behavior is undefined. Meaning, if you do this, you have no more rights to expect that your program works. It may appear to work, it may crash, it may do, I don't know, it may format your hard drives and then crash, it may do whatever. But you have no idea what's going to happen anymore. Or, if the argument does not match a pointer earlier returned by malloc, the behavior is undefined, meaning this provokes undefined behavior. Or, any use of a pointer that refers to free space returns in undefined behavior, meaning, if you do this, you don't know what's going to happen. Why is this so interesting? Because these type of undefined problems are described in documentation. They're not our bugs, or anybody's bugs. They are actually described as like, this is how you're supposed to do things. And what is the problem with this? Well, the problem with this is, well, let's see. What kind of documentation should any VM engineer read? Well, let's see. We have the IEEE spec. I can deal with that. Then there's since I'm writing C, I should be very familiar with the C99 and C89 specs that define what C actually is. That's 3 megabytes. And if I'm using GCC, I should read the manual for that too, and know it very well. That's another 3 megabytes. And I should also, since we have a VM that runs on Unix, I should know very well the single Unix specification version 3, that's 17 megabytes. And since we have a VM that runs on Macs, well, that's a 300 megabyte installer, I think it's compressed. I don't know how large MSDN is. And MSDN, let me tell you, it's not pretty. And so you think, this is pretty big. But in reality, it's more like this. That's the problem. Plus all the other things that are not even on that slide. So you see, you deal with things written in C and in this kind of environment, and it's really critical to read documentation and be very aware of what's going on. And to take these things very seriously, because if not, undefined behavior and appears to work. Or some things along the lines of, oh well, it works on my machine, so it must be the customer's fault because it crashes on theirs. It crashes in their production environment and they cannot reproduce it in their test environment, therefore it's their problem. Really? How do you know? Right. So let's take a look at a real undefined C problem. So here you have, basically you have two doubles, right? And two pointers to doubles, right? So first you say, well, let's see, get the address of double 2, treat that as a pointer, and assign 1.0 to the double pointed by the pointer. Then remember what the pointers are and copy the value referenced by the pointer 2, which would be D2 to D1, which is pointed by P1. No problem here. But now let's say that, because let's say you are implementing small doubles, you do it like this. Now a Q64 is basically a 64-bit integer. So this is basically the same. Look, there's hardly any difference at all, right? The only difference is the type of the pointer. Now this is a pointer. So this here is a pointer to a double, seen as a pointer to a 64-bit integer, and now the copy is done with 64-bit integer pointers as opposed to double pointers. And you think, wow, well, big deal, the addresses are the same, it should work. Let's color things for a bit. So see here, we write on yellow, we read yellow, and we write on red, right? So we would expect if we would disassemble this function is to see something like this, right? You write on yellow, you read on yellow, you write on red. Or if your platform is kind of funky and it happens with 32-bit instructions, you perhaps see something like this, right? Write, write, read, read, write, write. Everything's fine. Now, unbeknownst to you, C doesn't think this way. Because there's a rule in C that says no two pointers of different types will point to the same address. Meaning you cannot have a pointer to a double and a pointer to an integer point to the same address. Because that's wrong. Now the compiler will not tell you, hey, you have a problem here, and the runtime will not tell you, hey, watch out, or anything. It will just do it. But with the assumption that perhaps Q2 doesn't really point to D2. So really, this is a read, as far as C is concerned, from some other memory somewhere. And because of that, there's optimization. And perhaps the compiler decides, oh, let's reschedule the instructions because this way it will run faster. Or this way, or that way, or that way, or that way. They're all valid as far as C is concerned. And the problems that can produce are really nasty because whether the compiler decides to do either of those depends on the particular state the compiler is in. So maybe you change some code somewhere else, and that changes the register allocator somehow, and when it comes down to the time to compile this function, the register allocator is in a different state, and now you get different register allocation, different scheduling, your program doesn't work, and you didn't even touch this function. So, the right way to do it, according to the C spec and the compiler manuals is, well, okay, the C spec says that when you have a union, the members will be treated the way you would expect. So actually, you should write code that way. Even though it appears it's more convoluted, but actually it results in correct, from our point of view, execution. And if you want to do it in 32-bit chunks, then you do it like that. Now, if you don't see the spec, you don't see this. It's invisible to you. And perhaps, just by chance, you write it without knowing about the C spec, and the compiler produces code that appears to work for a while, until it doesn't anymore. So as you see, C is really not the same as Smalltalk. But then I hear you, right? You're going to say, oh, well, that's why there's so few of you VM engineers to deal with all this mess. But the problem is that it doesn't stop there. And that's what I came to realize. It doesn't stop at the VM boundary. It permeates the whole image. And this is where I get concerned. Because sometimes when I try to explain this to others in 5 minutes, I find myself at a loss. Because, we don't have all these pointer aliasing problems in Smalltalk and rounding and and huge specs to read. I mean, we have an image, we read all the code, that's it, right? But then it gets more complicated. Because, for example, well, let's say we do have a way in Smalltalk to call bits of C functionality. They are typically called primitives. And so let's say that we are taking a look at implementing primitives, so sockets. So one way would be with primitives. So of course, then you see, oh, well, socket write, you see some primitive, and oh, primitive failed, the usual thing. That goes to some primitive in the VM that says, oh, whatever, some OS dependent code, which myself, as an image programmer, I don't care, it's not my problem. And supposedly that has been written according to some documentation, and it's going to have defined behavior. Now, but typically, you don't look at the VM source code. So how do you know that the resulting sequence of operating system function calls that happen because you call these primitive methods comply with the specs of the operating system and result in defined behavior? Okay, let's say that, well, that's a VM engineer problem. Fine. But let's say, but you know what? Now I want to link to the socket library myself. So I'm going to get rid of the primitive, and I'm just going to use an FFI and call directly. Really? Well, how would you do this? Well, the first thing is go read the spec. So let's take a look at the spec. You look at the spec and you find out that there's this sock other struct that you need to call a whole bunch of functions, and well, you need to define this struct, and typically what you do in an FFI is that you have a method that says, oh, this structure looks like this, that, and that, has all these fields, all these members, and in this order, etc. So you go take a look at the spec, and what does the spec say? The sock other storage structure shall contain at least the following members: SA family T and SS family. But it doesn't say all the members, it doesn't say how big the struct is, and it doesn't say anything. In fact, it doesn't provide us with enough information to write what is the structure in a Smalltalk method. Because we as C programmers are not even supposed to know what that is. So immediately, we can't do this. This is just not right. But let's say that we decide to plow along, right? And see, well, okay, but how bad is this really? Well, that means that because you cannot define the sock other structure, you cannot call functions such as, accept, bind, connect, get peer name, get sock name, receive from, and send to, because they reference a structure which you're not supposed to define in your Smalltalk program, because the specification implies that those are private implementation details that you are not supposed to know. And it gets worse than that, because if you read the spec, it also says, oh, you know what? Those functions, they can also be defined as macros, which means that are you familiar with how macros work in C? All of you? Anybody doesn't? Quick recap, 30 seconds? Yes? Okay. So, when you compile a C program, the first thing that happens is that there's a macro preprocessor that takes macros, they basically look like functions, but they do text replacement on source code. So And that's before C compilation. That's just text mangling, right? And so the problem is that if you in C write something like accept, well, that macro, the macro for accept, will be evaluated before the function call for accept is evaluated or compiled. And so the macro for accept could rename your accept send as something along the lines of underscore private, don't ever call this accept, followed by 3, 5, 10 more functions and 5 more macros. And the problem with this is, well, you cannot call a macro from an FFI. So again, you can't do this. This is not good, because if you do this, let's say you do it anyway, right? You say, oh yeah, well, whatever, I can take a look at the .h files, find out what all the macros are, evaluate them mechanically, put them in Smalltalk, and it should work anyway. Really? I don't think so. Because let's say that you're doing this on Windows. Okay, so let's say that regardless of all these warnings, clear warnings that should tell you what you're about to do is going to cause undefined behavior and appears to work, you decide to do it anyway. And so, well, let's say that on Windows, for example, you decide, well, okay, so I'm going to go call some function, and if the function fails, then the MSDN says, oh, well, when a Windows function fails, typically you have to call getLastError to find out what happened. So basically this code says, oh, well, call the function. If it failed, say, oh, whatever, failure with getLastError. And you think this is perfectly fine, right? What could be wrong with this? It should work. It's doing what the MSDN specs says I should be doing. But the problem is that is not atomic from the point of view of C. Who says that the VM between those two message sends will not have to process some window event, have to request more memory, attend socket activity, file I/O activity, mouse activity, keyboard activity, and call itself getLastError? What? Because if that happens, then the value you get from the getLastError is bogus. And that can cause undefined behavior, like with sockets, for example. Because, let's say, for those of you familiar with sockets, because you would stop seeing errors such as E would block as a response to a read, and you would get, oh, there was no error, and yet you read 0 bytes. What does that mean? So now what? What do we do with this? So, as far as I've seen so far, there's this host of features of the C language that simply cannot be modeled reasonably by an FFI, like operating system calls, or linker macros, or compiler macros that you're not even supposed to know that exist. And because of that, in general terms, the only way to connect to a C program is to compile a bit of C code that is evaluated in the same compilation environment that was used to produce the C program that we are trying to connect to. Because if not, we are inviting undefined and appears to work. Now, it may seem imposing. At least to me, 3 years ago, it would have seemed imposing, right? Oh, why do I have to connect to C? I like Smalltalk, and Smalltalk is so much better, all that, right? I used to say that. I feel kind of ashamed because I've been so ignorant of all this until now. And now I feel I shouldn't be. I feel like I should be much more cognizant of this because I've seen the damage that this can cause. And so, what to do? So far, my point of view, and that of other coworkers of mine, such as Peter Hatch, with whom I've had a lot of conversations regarding this topic. I mean, he's been dealing with this for far longer than I have. Is that if you really want to do it right, you have to write a primitive, a small primitive. Because then you know you're going to get atomic C execution from the VM's point of view, so you're not going to have the problem of getLastError, etc. Plus, you compile your function calls in a primitive in a C compilation environment, so you're allowed to reference, say, SS family or whatever it is from socket, that socket struct, and the compilation environment will take care of that for you. And you don't need to care whether accept is a function or a macro, because the right thing will happen because you're compiling in C. And if the SDK changes under you, well, if the SDK was compatible with the old one, you don't have to change your Smalltalk code at all. It just works, because it is supposed to work that way. And in addition, you don't have to go and dig through endless .h files trying to figure out, well, what were these guys trying to do? In addition to that, there's an extra benefit. When you write a primitive, typically what happens is that you can make assumptions about the receiver, which is something you cannot do with an FFI, because there's no receiver, really. There's a C function. So typically what happens with an FFI is that when you call a function, you have to do all this marshalling for the arguments, right? Oh, this is an integer, right, but I'm passing a small integer, so I need to actually get rid of the tag bits and put it in the right order. And the next thing was a float. Oh, right, but that actually is a pointer to the data of the float, so actually I have to dereference the pointer, go grab the bytes from there, stuff them in the stack, etc., etc. And all that takes time. And with strings, right, so the string is actually a series of bytes that is somewhere, and hopefully it will not move, and it should be null terminated, and if it's not terminated, I have to copy it somewhere and null terminate it, and if I'm using UTF-16, then I have to null terminate with 4 bytes instead of 1, etc., right? So you can go through all of that generically, like typically happens with FFIs, or if the primitive is now implemented for a particular receiver, you can make assumptions as to what the shape of the receiver is. So actually, it may turn out to be that you can make assumptions, because you know who the receiver is this time. And so you can cut costs on marshalling. Because if you know what the receiver state is, then, well, you might as well store everything in a byte array, and then you have no marshalling at all. Because basically calling the functions means pretend that byte array is the arguments that need to go to the function. Copy all of that in the stack. Don't even care what it is, because it's assumed to be right. Go. And now it's faster. So, now I'm curious. Was this argument for paying more attention to C and the difficulties of talking with C convincing? Do you have any questions? Yes. I can barely hear you. Sorry.
What about the performance
Well, so what about the performance penalties and how we can get rid of them with the current approach of typical FFIs? Well, I know of one way in which arguments are marshaled for DLL calls, and basically the mechanism I'm most familiar with is that the image will compose a series of indicators of what type is which argument, encode that as some sort of bytes or whatever it is. And this takes time, right? Message sends like, oh, what kind are you, blah, 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 blah. Collect all this information from the image, send the primitive that says, oh, call this generic C function with all these arguments and with all these argument types. Now, when the VM receives this, it says, oh, what? Oh, okay, let's see. Oh, you mean this is an integer? Meaning you have a switch statement that says, oh, if this is an integer, oh, right, grab the first one and copy. Oh, what was the next one? Was it an integer? No. Was it a string? No. Was it a double? No. Was it a float? Yes. Ah, right. Nah, come on. It would be so much faster with an actual primitive that implemented the function call that you're trying to connect to, because then you don't need that. you know what the arguments are because they come in the right order and because you can assume the receiver, because it's not a generic C function call anymore. So that would be a way to speed it up. Then if there was a way to make this even more generic, then it would be interesting to see what a JIT could do to do the copying. But when you get down to a primitive of that nature, it might be that that's much faster already, and it doesn't warrant the complication of a JIT. Yes.
That's my understanding of yours. You say us some problems of the invisible virtual machine. In fact, it's not only about that virtual machine with C per se, because I would say to, okay, let's go to the miserable approach when you do a safer subset of C, and that will not others nor the tip of the iceberg of the problems we're talking here, because you have the PSP sockets that are on the last level, you have the windows that are on those levels. You're saying that we have a bigger problem than only the PSP.
Well, there's one example that comes to mind. There are, in some operating systems, there are two parallel implementations of the same functionality. Let's say, timers. And the spec may say you can only use one, not both. But let's say you just decide, let's pick one because I want to connect to it from the image because I need whatever functionality out of it. But the problem is, do you know if the VM is using the other one at the same time? because then, it appears to work, right? It's actually the behavior is undefined. I don't know how I'm doing with time. So, how does it look like? More questions, or that's it?
More questions are allowed.
More questions?
Any other question?
No?
No?
Okay, well, thank you.
Okay, thank you.